Okay, so we're going to look today at the concept of searching and sorting. So before I get into it, I'm just going to quickly talk about this. So let's say you had an array, and it was filled with random numbers. And I'm going to ask you guys right now to give me some random numbers, and please, whatever you do, don't give them to me in order. So what's the first random integer you can think of? -6. 7. What else did I hear? 4. We'll make it -4. 0. 102. One more. No, something in the middle. How about 3? Okay. So if I ask you to put these in order, if I asked you to say, okay, I want you to sort these into order, and you had to do this, what would be the way that you would do this? Describe your process to me. Okay, so in other words, what would I do first? If I was a complete and absolute moron, which is what the computer is, what would you do to tell it how to sort this? What would be the first instruction? What would you say? Take the first value, compare it to the one next to it. In what way?
If you're organizing from least to greatest, you'd see if the first number is smaller. If it is, then leave it there.
Yeah.
And if not, flip them.
Flip them, switch them around. Interesting. Does anyone have another method? I'll leave that one for now, because that's actually the least intuitive method, but also very correct. What's the natural way? First of all, what number is going to be first here? How do you know that? How do you know -6 is going to be first, other than the fact it's there now? How did you know -6 is going to be the first number when we sort it? That this -6 will be the first number in the new list. So I'm going to make a new list right here. How did you know, Zuhar, that -6 should go there? Because what? Well, how did you know compared to the other numbers? Now, how did you had to look at all the other numbers, though, right? So one way you could think that you did that is you scanned this list to find the lowest number, right? When you found it, which happened to be -6, you shifted it here. What would you do next? Would you do it again, what you just did? But in order to do it again, this one would kind of have to be no longer considered part of the list anymore, right? So now you'd scan the list for the lowest number. You'd find it. You'd shift it here. And then you would no longer consider that number in the original list. Then you would do it again. You'd scan the list for the lowest number. You'd find it. You'd shift it over. And you would continue this process, right? Scan for the lowest. Scan for the lowest. Scan for the lowest. And you'd have a sorted list at that point. But like anything, you need a way to stop this process, right? So if this process is being done repeatedly, you'd need a way to stop it. What stopped me from sorting this list? When everything was done, when all the numbers are left over. So some of these things you'd need to consider would be find the lowest. Okay, so I have to do that. I'd have to remove it from the original list. I'd have to copy it to a new list. I'd have to keep going while there's still numbers in the list. So these would be the kind of instructions you'd give the computer, is stuff like that. Those will essentially be methods in our solution. But now let's turn to Daniel's solution, a little more of an inventive solution, but let's see what this one would do. Okay, so I'm going to ask you guys for random numbers again. Please don't make the first number the lowest. Random number, please. 42. Next number. 3. 26. -9. 0. Good. Okay, so now Daniel has proposed a different solution. What he said is, start at the beginning and look at the first 2 numbers in the list. What he said is, if those 2 numbers are correct, in other words, they're in the right spot, then leave them alone. In other words, if they're not, one is not greater than the other, leave them alone. But if they're not, which they are not, switch them around. So in other words, the 3 goes here and the 42 goes here. Daniel, what would be the next thing to do then?
Check check the 3 and the 26.
Ah, so then this would move over. Like there, and check those two. And now, 3 and 26. But is it 3 anymore? No, because I just switched it. So it's really, this is now 42, and this is 3. So now is 42 and 26 in the right spot? No. So the 42 is going to go here, and the 26 is going to go here. So this is now 26, and this is now 42. Then what? I'd go to the next 2. And if they're in the right spot, I'd leave them. And if they're the wrong spot, I'd switch them, which I'm going to have to do. So negative 9 goes here. 42 goes here. And then we do it again. 42 and 0. Well, I got to swap them. Okay? So in the end, my list would look like this. 3, 26, negative 9, 0, 42. Is it sorted? Well, I got to do it again. Now, question. When I do it again, do I have to do the whole list? Do I? Is 42 in its correct spot? Will I have to go up to 42 again? So you're right, I'm going to have to go back and do this again, checking each one. But will I have to go to this one? No. In other words, the spot at which I stop at can stop there because 42 has shifted to its correct spot. And remember, 42 started at the very beginning, and it traveled all the way to the end. It found its correct spot. And the next time I go through, it's going to do these swaps again. And this time, that will be okay. These two will swap. It'll go negative 9, 26. It'll look at 26 and 0. Those two will swap. And then it won't check 42. But now look. Now 26 is in the right spot. So then the third time through the loop, I only have to go up to here. And each time I go through, I'll be one less that I'll have to travel through. So these are some of the things that we'll take into consideration. So I might have to swap stuff. I'm going to have to loop. Like these are some of the instructions that are going to go on there. Now, just like sorting, we're also going to look at searching. And really, there's only 2 main ways to search for something. And one of them is super, super easy, and you probably already know that. Okay? But again, I'm going to ask for some random numbers. Go ahead and throw them out. It's okay, I did it for you. So let's say I want to search this list for 13. See if 13's in that list. What would be the process of doing this? Okay, where do I start? Start at the beginning. Say, is this negative 13? Nope. Is this negative 13? Nope. Nope. Yes. So at this point, do I need to keep searching? No. I say yes, and I stop. Now, what's the result of a search? The result of a sort is that the list is now in order. The result of a search is there's probably 2 possible things I could send out of the search. One would be the answer yes. And what would that be in computer science terms? What would be a yes in computer science? A true or a Boolean. Right? I could make a search that determines yes or no is the 13 in the list. And let's say I search for 99. We'd go no, 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 and we're done. No, there's no 99 in the list. But what's another thing I could return other than just true or false? Ah, the spot. And that would be an integer. So in other words, it would give me spot 3, that this is at spot 3 in the list. If I send back true or false, when I'm searching with a Boolean, what would I send back as an integer if I'm searching for 99, which isn't in the list? What would be a good number to send back? Because I have to send back a number. Exactly right. Why -1? Right. 0 is not a good answer to send back because there is a spot 0. A huge number is not a good number to send back because it's possible we're searching a really big array. But a -1 would be a better solution. So I think you guys have the basic concept down of searching and sorting. So let's take a look. So most programs do in fact work with groups of data. You guys now have some idea about how that works because you've studied arrays before. We're going to be studying linked lists, which is another way to store groups of data, and other things that store groups of data. So one of the big parts of this is searching the list for important things that you need to find, right? So searching a list and then sorting a list are very important parts of what you'll manipulate your data when you do things for all kinds of programs that you write, okay? But in studying how to search and how to sort, it's not always just there's one solution. Entire university courses, entire university theses and master's programs are based around how to efficiently search and or sort a group of data, okay? So here's, again, the example. Here's an array, and if I'm searching for the number 48, or I'm sorting from lowest to highest, how would that algorithm look? How are the ways we can do that? So I'm going to present to you guys several different methods for doing this. And it'll also kind of refine some of the coding that we've been learning so far. Now, before I start in on our first search, the simplest one possible, I want to also just quickly show a classic animated example of this. And I usually find this online. I should have bookmarked it this morning, but I didn't. To show not the search, but the sort technique, and just some examples. Here it is. So this website, I love this look right here, okay? What is shown on the screen right now are these little lines, which could represent numbers. They're random numbers. So obviously the long lines are big numbers, and the little short lines are short numbers. So, for example, the algorithm that Daniel described is actually this one that we're going to study. And what I'm going to do is I'm going to click on it, and it's going to sort this list by doing the swapping that he described. So here you can see it actually in action. So it's slowly sorting this list. And it's done, okay? Now, that was a sort on a random set of numbers, right? A random set of numbers was sorted that way. Now, how would his algorithm work if the list was kind of already sorted? Wasn't quite sorted. Well, it would work as well. So here it goes. It would work that way. And how would it work if the thing was sorted but in the reversed order? Well, it would do it as well. But you can see here that his algorithm is actually fairly slow for that because it still has to go through piece by piece, even though it's already kind of sorted. Or one where this one says few unique. This means there's lots of duplicates. So it has lots of numbers that are the same in this list. And here's how it would go. Okay? So this is an example of that. And you can see it animated here. But this is one of, as you can see, several algorithms up here that implement sorts. So for example, let's go back to the random number one. I'm going to click here, and it's going to run, oops, all these algorithms at the same time. And that gives you an idea which ones can kind of get done first. And the one Daniel proposed was second last. So there's clearly faster algorithms for doing that stuff. But maybe that's not the case with this one, the neatly sorted. So now it's running that algorithm here, and here Daniel's finished much faster. So there's other algorithms that are still going, including this one called selection. It's still going. Or how about the reversed one? Here we're watching Daniel's algorithm in action, and it's pretty slow compared to the others right now. So that one didn't work out well. And then the last one, same idea. We're watching this one compared to the others. Some of the others are already finished, and his is still going. So overall, his may not be the most effective algorithm. Now, some of these are actually named the quick algorithm. So you'd think that those are going to be the fast ones. But it depends, right? And the neat thing about this little thing is I can actually run all of them at once. So it's running all the algorithms at once. And you can see some of these are already done. And some of them, you can see the slower ones are still processing. The thing is, speed should not be the only thing we should consider with algorithms. It should be an important thing, absolutely, but it shouldn't be the only thing we consider when we're writing an algorithm. Okay, so we're going to look at the linear search first. This is the simplest algorithm. It works by, as you said, proceeding from one element to the next until you find the one you're looking for. Oh, great, sound effects. So to look for 48, it will just say not found, found. Stop the search. That'll just wake you up in the morning. And here is the implementation that we're going to code in 1 second. So this is in the notes, and then a second version as well. Okay, so let's get started with coding this. And again, we're just going to get a quick start, then I'm going to jump over to the 11. So I need you guys to set up a project in NetBeans. And I'm going to suggest you call it something like searching and sorting examples. Searching and sorting. Okay. So I'm just setting up a project, searching and sorting. And I'm going to allow it to make a main class as well. Computer's pretty sluggish this morning, but it's crunching away and building up the project. Okay, so we're going to also build a few other little tools as well for working with this, including like we're going to obviously use an array, and we're going to sort and search the array. So we're going to be using a number of classes that we're going to be building. I hope that these classes will also be stuff you can use beyond just this example. And a classic, this happened in the last unit too when we did files. I built it so that there was stuff you could reuse. And I'm going to try to encourage that as well here and just sort of encourage some good programming practices. Okay, so searching and sorting example. Okay, so we're going to manipulate an array. So I'm going to just make first a final int size equal to, and I'll just set it to 15 for now. So we can later just manipulate the size of that quite easily. So if we want to search or sort an array of size 150 or 1050, we'll just change the number right there. At some point, we'll be searching for an item. Okay, I'm just going to set it to 0 for now. And we will be searching an array, which I'm just going to set to null for now. So I'm just setting those up. So in a minute, I'm going to give the array a value, and I'm going to give the item a value. But they're going to be random values, and then I'll sort them and search them and stuff like that. But for now, I'm just setting them up so that they're ready to go. Okay? So these are our needed items. Okay. So now I will give my items random values. You don't have to put the comments in, but so item will come from a random value. Okay? So I could write the whole random number formula thing here, but I think it's time to actually build a useful class for doing this. Okay? So I'm going to make a class called NumberTools. Now, the second you type that in, NetBeans will have no idea what you're talking about. What's number tools? I put a capital N on it because it's going to be a class. Luckily, the light bulb will help you here. And it allows you to kind of, hopefully, build what I want. I'm surprised it's not giving me the option that I thought it would. I actually need this to be a class called number tools. So if you get the option with the light bulb to create the class, go ahead and do that. But I'm actually going to have to manually create a Java class called number tools. Okay? So there's my class called number tools. So now it knows what number tools is. Dot. And I'm going to make a method within that class called random int, which is the random integer method that I'm going to write. And I have to give it a low number and a high number. My low number will be negative size, and my high number will be size. So what I'm hoping is going to happen here is it will generate a random number between negative 15 and positive 15. This isn't for you guys. This is for the 12s. Oh, okay. I just went, well, we'll do that, okay? So just one sec, because I'm almost done. To make a class, you go File, New File, and then Java class, right there. Okay. We'll get to that method in a minute. You can also use the light bulb to create the method for you, and it will go right into number tools and build the basic structure of that method. But we're not quite done yet. As well, we're going to say array equals number tools dot create random array, and I will give it the variable size. So this will be another method inside of our random tools class. It'll generate an array of this size, whatever the size is, and we said 15, and it will fill it with random numbers. So I'll have a random number to search for and a random array of values to search through, if those two methods work. So I'm going to create the method there. So that will just set it up, and then from here I will search, which we won't have time for today. But the reason why I want to make those as methods within a class is we're going to do this over and over again. We're going to randomly create a number to search for, and we're randomly going to shuffle the array with new numbers, and then we'll implement different searches. So it's not the same array we're searching through each time. It'll be a different array. It'll be a random array. Okay. So real quick, let's just try to punch off these two methods within our class. Now, it does not automatically put the keyword public at the front of the method. I suggest you do that. It's not necessary, but I suggest it. One interesting thing it put there is the word static. Okay? I'll go into more detail what that means on a different day, but that's just a nice feature that allows you to not have to instantiate the number tools class in order to use its methods. I know. Okay, I'm also going to rename these two parameters. This one's going to be renamed low, and this one's going to be renamed high. Because that's what it's doing. It's a random number between low and high, and this one I'm just going to rename just size with a lower case. Okay. We've done the random integer method before. Basically, you can use the math class to create a seed value equals math.random. That's a random seed value, and then I can create another double for the low by casting that integer as a double. By the way, there are other ways to make random numbers other than this method, but I like this method because it requires no imports. Equals the double of high. So I've casted the two integers into doubles. Then I generate my random by using the strictest random number formula, high minus low plus 1. Now, here's a weird thing. At this point, everything is a double. H is a double. This is a double. That's a double. But 1 technically isn't a double, right? 1 looks and kind of acts like an integer. There's a way you can make Java think it's a double, which is, you might think is just put 1.0, but it's not quite. What you do is what you put beside the 1 is the lowercase d. What that does is it's a little shorthand method to Java that says that constant 1 is a double, okay? Times our seed value plus our low value. High minus low plus 1 times the random number plus low will generate that random number. But I need to return it as an integer because my method uses integers. So I'll return, and at this point I'll cast that random value as an integer. So it, at the end, turns it back into an integer. So that's a very simple random number formula. By the way, it doesn't have to be 5 lines. You could actually reduce this down to 1 line if you wanted to, but you have to do some factoring to do that. But there we go. Okay, so now I want to work on this method. I want to create a random array. So let's make one. I'll make an int. I'll just shorten it to A for array, equals a new int of this size. And I will eventually return that A. That array will be returned from this method. So that would generate the array, but it's an empty array at this point. So in between, I'm going to use my for loop and loop from 0 to size and say A spot I equals, I can use my random int method between negative size and positive size. So that will generate the random array. Okay? So it will automatically generate the random array, and it will automatically generate the random integer. So real quick, just to test this before we wrap today, I'm just going to write in a line here. I'm going to output what the item is, just to see that it's a random number. And I'm going to output what the array is. And believe it or not, Java can do this. It can output an array directly. So I'm just going to run that real quick and show you the output. As I should be getting random numbers between negative 15 and positive 15, hopefully. And upon a run, we get that. So it doesn't quite output the array the way you'd think, right? That's a weird array. What that actually is doing is outputting the memory address. Let me just try something real quick. That's not going to work either. Yeah, I didn't think so. Okay, so we can't output the array directly like that. We have to kind of make a method for that. We have to make a method to output it. So we'll do that tomorrow. Okay? Okay, so yesterday we ended here. We didn't really start any of the searches and sorts yet. We're just setting up for it. And there's one other thing we need.
Attention staff, just a heads up, the power school is up here in the office, and so is first class. Thanks.
Okay, so one more thing we need is because we're doing a search, we need the location when we search for something. So grade 12s, I want you to add one more variable up to the top here. So we have the item we're looking for, the location we'll find it at, and the array we're going to search through. So we forgot that variable, the location, okay? Because that's going to be something we're going to be figuring out whether or not we found it or not, right? So, okay, that's interesting, but I don't know. Okay, so now we're going to perform the search. But before we do, we should output what our array looks like, right? And we talked about that yesterday, how you can't just do that real simple with the system.out. So once again, I'm going to build a class to do this, just to encourage you guys to do that. I'm just going to make a class called display. So to display stuff, dot, and I'll make a method within that class called, what? Someone's trying to skip this version. Inside that class, I'm going to make a method called just show. I'm going to keep it simple. Display.show, okay, and I will display the array. Now normally, like I said yesterday, you can't just send a whole array to system.out. So I'm going to build this into a class just so it makes it easy down the line. So let's build this class, create class display. So it should make you a class called display. Very simple. And then you can jump back. Wow, computers are really slow today. There we go. And then jump back to your main class. And then you can also use the light bulb to create the method called show. Okay, so the show method inside our display class will show off a whole array. Okay? So this is very simple. We'll just loop through the array. So array.length. Oh, lots of spinning circles today. Lots and lots of spinning circles today. Whoa, that's an interesting look there. Okay, so now we're looping through the entire array. We're going to output the stuff. Now, we could output the array line by line, but that's going to take up tons of space. So I'm going to back up here and start by making a string called output equal to, and I'll just put array equals. I'll even put a little bracket thing there. And then I'll say outputs plus equals. Remember, that means output equals output plus what's in the array at spot I plus a comma, okay? And then afterwards, I'll output output. And at the very end, I should probably put that closing bracket so that'll look nice. But one weird thing about this, just to show you what will happen here, is it'll loop through the array. So say an array of 4 things like this. 0, 1, 2, 3. It'll loop through the whole array and it'll say, like say I had 4, 5, 6, 7. It would go 4, 5, 6, 7, comma. Which is weird because there shouldn't be a comma after the very last number. So let's just make a little tweak to this code to make it output a little bit prettier. Make it go to array length -1. And then after the for loop, then go output plus equals array spot. Now here I actually need the very last spot in the array. So to get that, I go array.length -1 here. Plus that closing bracket. And a new line character. We'll just put a new line there. Or actually, no, we won't because we're going to do system. We don't need to put a new line because we're doing print line. So this should spit out our array in a nice format. So I went quickly through that code, but I just want to play it just to show you what it looks like real quick. Because we're filling that array with random numbers. It'll be nice to see how it looks when I output it. So, come on. There we go. So you see how nice that is? It makes it look like an actual array with the little brackets on each side. So that'll be a nice way to quickly output an array as we do these searches and sorts. Okay? And again, this might be something useful for your debugging if you're writing code and you're just doing displays. You can just quickly display what an array looks like just so you can see it inside your code. So again, I'm sort of encouraging just building little classes that can be useful in the future as you work through this. Okay. Now, if we go back here, sorry, was I too quick? Anyone still need that code, the display code? So watch those little quirks like the -1s that are occurring in those couple places. Jumping back here, we show the array. What we're now going to do is we're going to make a class called search tools dot, and we're going to write our first search, which is the linear search, and we're going to search for our item, comma, in our array, and it will return something. So on this side, we will put our location equals this. So in theory, what's going to happen is it's going to go to this class, it's going to run a method called linear search for this item in this array, and it'll send back a location. Okay? So now we got to build the class, and we can use the light bulb to do that, called search tools. So it should automatically build that class for you, and then jump back to main and go ahead and use the light bulb to automatically build the method called linear search. So that's just a handy way to just have NetBeans write some of the code for you. Okay? And I'm going to put the keyword or the modifier word public at the front of the class and the front of the method. Okay, so now I'm in search tools. So I'm in this class called search tools, and I'm about to execute the algorithm for a linear search. This is by far the simplest algorithm. How do I search an array for an item? Well, it's real simple. I loop through the array. Yeah. Okay, so I'm just going to use the loop. For I equals 0, well, I is less than array.length. Oh, man. Okay. If, so inside the loop, if the array at spot I equals my item, well, then I found it. So I return right here, and what I'm returning is the spot. So I'll return I. That's the spot. That's the spot I found it at. However, I've got one other thing to do. It is possible that I will loop through this entire array, and this will never become true. I will never find the item. So if it makes it through this whole loop without ever returning, just at the bottom of the code, right before the method ends, I'll return -1. -1 will tell me that I didn't find it. Okay? This is the simplest algorithm, and I know it's not that complicated, and you've probably maybe even written something like this before. The linear search is as simple as it gets. You start at the beginning, and you start looking through each item. If you find it, stop and return right there. Now, remember, if you return while you're inside of a for loop, it breaks the for loop. So by putting the return line there, it would finish that method at this point. So that is the simplest algorithm for doing a search. The linear search for an item in an array. So I just missed the screen recorder there for a second. So at this point, just to finish up for today, we have this class called display, and we wrote a method called show results of the item in the location. So this will show the results of the search, and the method we wrote inside the display class that says show results basically says if the location equals -1, or sorry, pardon me, if it's not equal to -1, we will output item was found at location. However, if it does return a -1, then we will output item was not found. Okay, so this will show the results of the search, and let's run it once just to test it. And here you can say that it says -8 was not found. So the value -8 should not appear anywhere within this array. And if you scan it over, you'll see that that's true, that -8 does not appear in the array. But if I run it again, and again, and I'll have to run it a few times until I get one that I don't want to use that one. Here we go. So now with this one it says negative 14 was found at location 14. How ironic. So let's see if that worked. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And there it is. Found the 14 at location 14. So the search was successful. Okay, and we'll pick up more on this tomorrow. Okay, so before the break, this is where we started our searching and sorting unit. We set it up by creating a few variables that we're going to use all through the example. So we have a size variable that will control the size of the array we're going to use. We have an array that we set to null to start. We have an item, that's the thing we're going to look for, and the location is where it will find it. So right now we're just setting all these things to just null values and just 0 values just to get ready. And then we used some methods and classes to assign them values. So the item comes from a class called numberTools, and we generate a random integer. So we basically say, here's a random number to search for. We generate an array from the numberTools class as well by creating a random array. So the numberTools class is just a little class that helps so that we don't have to put a whole bunch of code right in our example. And here you can see in the numberTools class, we made a random integer method. We've done that before. And we made a random array method that calls the random integer method. That just generates the array full of random integers. And then what we did after that is we showed the array, and we did that through a class called display. Again, just to optimize our code a little bit, we made a little class called display, and it basically has two methods: show, that just outputs what the array looks like, and show results, which will be something that will be useful for searching. So when we do searches, it'll say item was found at location whatever, or if it returns -1, we'll say that the item was not found. So that's done, so that it just optimizes our code. So we say display the array, then we say search for the item in the array, and then to show the results. Now, what we did then was we put our search into a class called searchTools, and we used the first search algorithm, the linear search. Okay? So this is where we left off. Where I want to go today is our first sorting algorithm. Okay? So what we had right here was our linear search algorithm. Now what I want to do is our first sort, and it's called the bubble sort. So what I want to do is I'm going to repeat some of this code. I'm going to re-randomize the array. So I'll just do that. So that will create the array again. So it's created again. Okay? And then I will show the array again. Okay? So I create the array, I show the array, and then I'm going to show it again, but in the middle, between the two displays of the array, I'm going to do a sort. Okay? I'm going to do a bubble sort. And I'm going to do that using a class called sortTools.bubbleSort. And I'm going to pass it the array to sort. Okay? Now we don't have that method yet. Okay? So we don't have a method called bubble sort. We don't have a class called sortTools. So we're going to build both of those. But another nice thing that's going to happen, I hope, when this is done, is it's going to show that the array is now in order, like it's sorted. Okay? So I think I'm going to just quickly overload the show method as well, so that I can tell the difference between the two arrays, a regular array and a sorted array, by just putting the word sorted in front of this. Okay, so I'm going to have to make a couple changes to my code to fix that. Okay? So here again is what the code is we're going to start with today, is these 4 lines of code right here. Okay? So we recreate the array. That'll just re-randomize it. We show that array so the user can see what it looks like. Then we will sort the array and then show it after it's been sorted. So the first thing I want to fix is I want to go to the display class and overload this show method. This is going to be very, very easy. So I'm going to use the light bulb to do this, or you could just go directly to the display class and write in the second version of the method called show. Okay? Okay? So really, all I'm going to do is the same thing I did before, basically the same code. So I'm just going to copy this code, put it here. So it's almost identical. Okay, so all I did was I copied all the code from show into this version of show. So it's the same basic method. And I'm going to switch the name of this parameter right here to type. And I'm just going to do that. So let me highlight again the changes I made. I made a change right here by putting in the word type there instead of the word sorted. And I changed this line right here, right there. Those are the changes I made. Other than that, the method stays the same. Now, I probably could modify both of those methods to make things a little more optimal, but I think this will work for now. This will be fine, okay? Okay, anyone not got that? Very simple change. Okay, don't try and run your code yet because we still got a major error. If you want to run it, you could comment this line out for now. And then if you tried to, it should still run that way. Okay, so again, you can see here now the only difference is this one will say sorted, whereas this one says array, right? This one says array and this one says sorted. That's the only real difference. Okay, and what we're going to see, hopefully, is that this will now be in order when it runs, when we get that part working. Okay, so now let's go back to here. And now let's build this class called sort tools. So you can use the light bulb to do this. Create a class called sort tools. And it should automatically just generate the class for you, which is nice. Then I'm going to go back again, and now I'm going to use the light bulb to generate the method called bubble sort. And it should generate the method for me as well. Okay, so very handy. You can certainly code all that yourself if you want. But it's easier if you use the light bulb. Now, what we're doing is we're passing an array to this method. We're passing to it to the method within the class. Now, what's going to happen is the method is going to switch things around inside the array. It's going to shuffle positions around. So when this method is done, the array will be changed. And that's because arrays, when they're passed to methods, are passed as the entire array, as a reference to the array. Not a copy of the array, but the actual array is passed to the method. So anything that the method does to the array will be reflected after the call of the method is done. Okay, so now I just want to real quick review what this method, what this bubble sort does. We talked about this briefly before spring break. So I'm just going to review that with you guys real quick. Oop, I guess I got to put this in there for that to work. Okay. So what the bubble sort does, okay, is it moves through the list, essentially bubbling items to their correct position, okay? It does this by swapping items, okay? It compares one to the next, and if they're in the correct order, it leaves them alone, and if they're not in the correct order, it swaps them, okay? The result of this is it will bubble things to its position. So I created a real quick little animation for this, just to sort of demonstrate. So here's an array. It checks the first two. They're not in the correct order, so it swaps them. It switches them around. So now the 4 and the 17 are swapped positions. Then it goes to the next two items. So now the next two will be 17 and 8. So it looks at those two, and those aren't in the same position, the right position. So it'll swap those two. Then it'll go to the next two, which is 17 and 24. Now 17 and 24 are in the correct position. 17 and 24 do not need to be swapped, so they're left alone. But then when it goes to the next two, 24 and 1, those will get swapped. Okay, so they'll get switched around. Okay, now it has now gone through the entire array. Okay, it's looked at each pair as it went through. It's not sorted yet, but it's closer to being sorted. So what it's going to do is it's now going to repeat that process. It's going to go through the array again and continue to swap items. How many times do you think it would need to go through the array to do this? What would be like the worst case scenario? That's right. 5 is right. In other words, the amount of items in the list would be the worst case scenario, right? So if it was a list of 500, it might have to go through it 500 times, right? So that's right, okay? And et cetera. So I've got more sort of animations that sort of demonstrate this, but you get the idea, I think, right? Okay? So let me get through that. Okay, forget that. Let's code this. Okay, so in order to travel through the array, we need a for loop. Okay? So remember, you can quickly type in a for loop, if you want, by just typing FOR and then hitting tab. Now the array does not, or the loop does not go from 0 to 10. It goes from 0 to array.length. Okay? Because we don't know how many items are in this array at this point. Okay? So that will, first of all, do what we asked, to travel through the array. But then we're going to need to do that multiple times. So what we're going to need here is a second for loop that goes through array.length. Now, if you use some of NetBeans' auto features, it will name these two variables I and j. It is very non-creative about naming these variables. That's fine. I'm okay with those. Those are fine names for variables. I is traditionally used in loops because it stands for iteration or index. Either of those is fine as it loops through the array. J is picked because it's the next letter after I. That's really the only reason they picked J. So now, inside the loop, what we're going to do is we're going to compare by using our if statement. If the array at spot j is greater than what's in the array at spot j plus 1, in other words, the next spot over, we will swap them, which I'll write the code in a minute. We will swap those two values. And that's it. Really, that's the whole algorithm. But there's a couple potential errors here. Okay? So let me draw out what would be happening here by just drawing a little array right in front of us here. Spot 0, 1, 2, 3, 4. Can I have a random number, please? Another one. Make it -6. Another one. Another one. 28. And we'll make that one 401. Okay, so there's a random array. Okay, so let's think about how this is going to work. It creates a variable called I, sets it to 0, creates a variable called j, sets it to 0. Right? That's what the two loops do. Now we're inside the inner loop. We're looping just with j. So it looks in the array at spot 0 and spot 0 plus 1. So it compares these two values. If this one is greater than that one, which it is, it would, when we write the code, swap them. So in other words, this will now be -6, and this will be 10. So far, so good. Then it would stay within the inner for loop here. So in other words, now j would go to 1. And now it would compare spot 1 with spot 1 plus 1, or in other words, spot 2. These are not in the correct order. So it would swap them. This would become -17, and this would become 10. And then j would go to spot 2. Okay? It would compare spot 2 to spot 2 plus 1. These are in the correct order, so it would leave them alone. Okay? Then it would go to spot 3, right? So you can see here, it keeps going, so it goes to spot 3, and it would compare this one with this one, spot 3 and 3 plus 1. And those would get swapped, 28, 401. But here's where the error hits. It would now, because I'm looping to array.length, less than length, the length is 5. What's less than 5? Well, 4 is less than 5, so it would go to spot 4, which seems to make sense. There is a spot 4. Here's where the error hits when it compares spot 4 to spot 4 plus 1. There is no spot 4 plus 1. So this will right away cause an error. So let's fix that. That's an easy fix. We'll go to 1 less than the end of the array. So in other words, we'll go to this minus 1. Whoops. So that should fix that. Now, let's perform the swap. Now, every year I use this demo to try and identify the swap. Okay, so I'm going to use this cup right here, this beautiful trophy cup, and this coffee cup. Okay, here's what I want to do. I'm going to put a Kleenex, and let's imagine it's full of Kleenexes, in this cup, and this one obviously is full of pens. What I want to do is I want to put the pens in there, and I want to put the Kleenex in there. How would you do it? Maybe I should put it this way. Forget the pens and the Kleenex. Let's say, let's use a more liquidy example. Imagine that this cup is full of coffee, and this one is full of Pepsi or Coke. How can I get the Coke in here, and I can get the coffee in there? Anyone got an idea? 2 other containers. Ah. Now what was suggested to me last semester was just drink the coffee, pour the Coke in there, and then spit the coffee into there. But you're doing the same thing, okay? Usually I also have some smart aleck kid who will say, well, you can actually do this, Mr. Walks. Just throw the Coke up in the air, quickly switch them, and then they'll catch both of them in the same thing. Doesn't quite work. But it's also something you can think about in math. Like, what if I did this in math? What if I said x equals 5, y equals 7? If I wanted to swap those, can I just do this? X equals y, y equals x. Does that work? What's inside of y right now after the end of that run? If that was actual code right here. Think about it. This is x, this is y. I just said x is 5, y is 7. The next line says x equals y. So this becomes 7. And then what does the next line say? It says y equals x. And what's x? 7. Now they're both 7. In order to swap 2 things, you need an intermediate variable. You need something to hold on to something in the meantime. So that's exactly what we're going to do with this little code right here. So here's what we're going to do. We're going to make a variable, a little integer to hold on to it. Let's just call it, I don't know, swap equals array spot j. So that's holding on to what's in spot j right now. So now I can replace what's in spot j. Array spot j equals array spot j plus 1. Then array spot j plus 1 equals what? It equals swap. That's right. It equals our temporary variable. So that performs a traditional swap algorithm right there, to swap the contents of an array from one spot to the next. And if that works, this should be a working algorithm. Let's try it. I'm going to run the code. So here's the original array, 3, negative 10, 4, negative 2, blah, blah, blah. And look, here's the sorted array, negative 10, negative 9, negative 8, negative 5, 4, 3, all the way up to positive 15. It worked. It sorted the array. Now, it actually did it pretty fast, too. So I'm going to jump back to this one, and I'm going to push this computer. Let me try 150 items. Done. Took 0 seconds. How about 1,500 items? Done. 0 seconds. How about 15,000 items? Oh, there was the search. By the way, it's performing a search as well. 6 seconds. Took 6 seconds. But now you can see what's happened. We just generated 15,000 random numbers and then sorted them. Impressive. That's some impressive code right there, I think, that you guys should be impressed by. Okay? Did anyone not catch that? Any of that code missing for anybody? This is the basic bubble sort algorithm. It is very basic and not efficient, believe it or not. It works. It will sort an array, but not in the best of ways. It's not the most efficient of ways to do it. Okay? So we're going to modify it slightly. We're going to make things a little more efficient. Okay. Just one sec. Okay. So that's right. Once it's in order, it doesn't stop. So that's the first inefficiency. There's a second one. Okay? The second inefficiency is this. Let me just show you. I'll put a pretty small array. Okay, so let's say this was the array. Watch what happens with 400 right now. Okay? 400 would be swapped to here. Then it would be -6 here, 400 there. Then 400 would go to there. So the 400 would be there, the 5 would be there, right? And the 400 would be there. Then it would compare it, and it would go to there. So the 400 would wind up here, the 2 would be there. What happened was the 400 bubbled to its correct location. The 400 is now there. The next time it goes through this loop, okay, it'll compare this to this. They'll be fine. It'll compare this to this, and it'll swap them. The 2 goes there, and the 5 goes there. But here's the question. Does it need to compare these two? The answer is no. Once 400 gets to there, it's in its correct spot. And now that 5 has got to here, it's in its correct spot. The next time I go through this loop, I will not have to compare those two. So in other words, every time it loops, it'll put one of its items in the correct spot no matter what, so that the next time we loop through, we don't have to do that. So here's how we're going to optimize our code. This will make it a little more efficient. Okay? What we're going to do is we're going to modify that first loop up here. And instead of looping forwards, we're going to loop backwards. In other words, we're going to start I at array.length -1. Start I at the end of the array. And keep looping while it's not this, but greater than or equal to 0. So this will now be a loop that goes backwards. So instead of going I++, we go I minus. Now, what this will do is it'll start at the end of the array and move towards the beginning. So I change this part right here. Notice the -1. I change this right here. Notice it says greater than or equal to 0. That's because there is going to be a spot 0 in an array. And I change this part to be minus, because we're now going backwards. Now that really doesn't seem to make a difference at this point. It's still the same number of loops, right? Still the number of iterations. But the big change happens now on the inner loop. On the inner loop, now I change this to I. Okay? That makes a huge efficiency difference, because now with I there, it will loop up to whatever that value is, and that value will change every time it goes through the loop. So it reduces the number of comparisons it has to make. So that made the first correction. The second one is the one that Stephen pointed out. What happens if it's already sorted? Okay? Well, let's take care of that. We're going to take care of that by creating a Boolean variable called sorted. And we're going to assume that it's true, that the array is in fact sorted. We're going to set it to be true. We're going to assume that the array is sorted. Okay? We're also going to set it to true after the first loop. So this is going to flag that we're going to assume the thing is true before we head into this inner loop, right? So we're going to go, remember, it's this inner loop that actually goes through and does the swapping. This outer loop just counts how many times to do it. So we'll assume, you know what, I'm going to assume that this thing is sorted. But if at any point I perform a swap, if I perform a swap, then it's not sorted. I had to swap something around. So if it's not sorted, in other words, if I swap something, I got to keep going. So at this point, I set sorted to false. Notice how I do that inside the if statement. Inside the if statement, if I make a swap, I better go through the array again. Now, one more line. After this for loop here, after this for loop is done, before I go back and try and do it again, I check, well, if it's sorted, I'm done. So at this point, I can just return. That's a way you can break out of a loop, even though I'm still inside this outer for loop. So even though I'm inside this for loop out here, if it's sorted, I can hit the return command, which breaks out of the method completely, including breaking out of the loop. So this was the inner for loop, right here. So in other words, I assume that it's sorted, but if at any point during this inner for loop it performs a swap, I say, oh, no, it's not sorted. So then when it comes to here, it won't return. It'll go back and perform the operation again. This has now fixed those two inefficiencies. This bubble sort is now a more efficient bubble sort. It will still work. You can see there. Let's see if it actually makes a difference. I'm going to set that back up to 15,000 again. Who remembered how many seconds it took the first time I run this? No, at 15,000, 6. So in theory, this should be a little more efficient now, okay? Seven, less efficient. Now, it could be the numbers that it ran. I'll try one more time. But in theory, it actually is more efficient. Now, I didn't prove that to you guys at all, did I? 5 seconds. There, it was 1 second more efficient that time, okay? Okay, but the efficiency of algorithms is actually an entire realm of computer science that we're just scratching the surface on. Just getting it done is like, I heard a great quote, did I tell you guys at the conference? So I'll apply it this way. Writing code to just get it done is like using duct tape. It can fix anything, but probably shouldn't be used for everything, right? You can't just write code always to just get it working. Although I understand that. I understand that sometimes that's the case. But sometimes you have to think deeper what's more efficient about this code. Okay, the bubble sort is now complete. But now we're going to take a look at something else, okay? We're now going to look at a second type of sort, okay? So we're going to go back to there. Bubble sort's done. And now we're going to look at something called the selection sort. It's a different algorithm. So it's basically going to have the same 4 lines of code. So I'm going to put them in there. The only difference is right here. I'm going to write something called selection sort. Okay, so we're going to put that method into the sort tools class. And again, the reason I'm putting them into classes is that so you guys can break your logic up. If you want to use something like this for your final project, you've got the code ready to go. And it's not buried within some large example. You've got the code in a specific place. It's in a class called sort tools, which is easier to find. So now we're going to recreate this scenario. We're going to just show the array. We're going to sort it, and then we're going to display the sorted array, okay? But this time we're going to use a different algorithm to do it called selection sort, okay? So let's do that. Let's use the light bulb. Go to the sort tools, and now let's take a look at selection sort. Now, selection sort is actually an algorithm that you came up with more naturally. This is the more natural way to sort things. We don't normally think of sorting things by switching positions and doing swaps. So this is actually a more natural algorithm, but it's, believe it or not, harder to code than the other one. So again, the idea is, what you do with this algorithm, it's the way you sort things normally. You look for the lowest item, you take it out, and you start putting it into a new list, removing it from the original list. And you continue this until all the items from the original list are gone and the new list is created. So here's the example. This is the way we sort naturally. We look through this list and we find, for example, the smallest item. So we look through it, we go, what's the smallest item? Okay, It's that one. So I'll move that one to the new list. But think for a minute how that worked. In order to find the smallest item in a list, I had to look through the whole list. It's possible that the lowest item was at the very end. I don't know until I've looked through the whole list. Now that I've copied it over to the new list, it can no longer remain here. Because otherwise, if I try and do this again, I'm going to find it the second time. So I have to remove it from the original list. But now I repeat the process. I look through, find the lowest item, copy it over, and I can continue this process, looking and copying, until there's nothing left in the original list. Once there's nothing left, I'm left with now a sorted new list. Okay? So this is how we're going to do it, but to do this, we have to kind of make a few adjustments. How do I delete something from an array? How do I make a new list? How do I know all these things? So we're going to do that. We're going to incorporate that into our logic. This is the pseudocode on the selection sort right here. The pseudocode is allocate a duplicate array to store the value. So I create a duplicate array. Loop, while there's still values in the original array, find the lowest in the original and remove it, add the lowest to the duplicate at the first available spot, and then copy the duplicate back onto the original. Wow. Let's do this. Okay. So I'm going to make some assumptions with this code that we're going to be using some methods. We'll make the methods later. So the first thing is we have to make a duplicate array. I'm just going to call it duplicate. Equals, and to do that, how do I make a duplicate? Okay. Well, I will make a method called create empty duplicate. And I'm going to pass it the array because that's what I'm making a duplicate of. I'm making an empty duplicate. So in other words, it's not a copy of the array because I want it to be the same size as the array, but filled up with empties, whatever that means. We have to figure out what that means. Now I'll hit a loop. While not empty, while what's not empty? Well, while the array is not empty. Okay, and again, we'll make that method. The lowest value, so I'll make a variable called lowest, equals find lowest. But I'm going to try and do two things at once. I'm going to say find the lowest and remove from the array. So I'm going to find the lowest thing in the array and remove it. And then I'm going to add to the back the lowest value. I'm going to add it to the back of my duplicate. Again, these are all methods we're going to build. Just basically doing the pseudocode here. And then finally, when the loop is done, I will copy the duplicate onto the original array. And so in theory, then the array will be sorted because it'll become the duplicate. So this is the pseudocode behind this. This is, again, a way you can program by thinking methodologically of what methods will perform the operations that I want them to perform. And now I'm going to go in and take care of all these methods. So I've got to write 1, 2, 3, 4, 5 methods right now. These 5 methods will all be private methods. They'll be just inside the class, utility methods that will help get this job done. I won't need them necessarily outside the class because this class is supposed to focus just on sorting. It's not supposed to do stuff like removing from arrays. So these will be little private methods. Okay? Anyone not get those? So let's start with the first one. Create empty duplicate. I'm going to use the light bulb and create it. Okay? And then I'm going to go and use the light bulb on the next one, not empty. And then the light bulb on the next one, find lowest and remove. And then add to back. And then finally copy. Okay? So in theory now, although all these methods are empty, they will perform the operation selection sort. So now selection sort in theory is done. But we got to fill in the blanks of these things that We're left blank at this point. Okay, now they're not that bad, most of these methods. They're not that long, okay? So let's start with create empty duplicate. To do this one, I make an int array that I'm going to call duplicate. And it's equal to a new int, and the size of it is array.length. So it matches the length of the original array. At the end of this method, I will return the duplicate. Okay? So that looks pretty good. That would actually do it, but duplicate will now be filled up with zeros. Right? When you create an array, it's going to be filled with zeros. And the problem with 0 is it could be a valid number. I need a number that's really uncommon. And 0 is way too common. So I'm going to have to kind of cheat a little bit. Now, if this wasn't a primitive data type, if this wasn't integers, if this was something more complicated like strings or a class that you made, an array of your classes, you could use the value null. That's a perfect thing to represent an empty spot. But because it's type integer, you can't use null. Null is not used with primitive data types. So I need an extremely rare integer. Can you name such an integer? Of course you can, because they're all, if it was extremely rare, you wouldn't be able to think of it. But I can think of it. It's built into the class called integer. Notice the capital I. And there are two really rare ones, the maximum value and the minimum value. These are two extremely rare. They're as basically as big or as small as the value of an integer can hold. So for example, for max value, it's 2 to the power of 31 minus 1. That's a pretty big number. And for min value, it's negative 2 to the power of 31. Again, notice there's one difference there, but we talked about that back in grade 10. Extremely rare. That's going to represent, for me, an empty spot. So what I want to do is fill up my array with that. So I'm going to use a for loop. I'm going to loop through duplicate.length. And I'm going to say into duplicate at spot I, you're equal to integer dot min value. So I'm going to fill it up with extremely rare values. That's how I create an empty duplicate for me. Okay, and it's a bit of a trick. It's not the most efficient code. I'm going to show you a more efficient way to do this later. But for now, that should get the job done. That should fill it up with temporary integer values. Okay, the next method we're going to work on is this one called not empty. So what not empty is going to do is it's going to look through the array to see if there's anything still in it. So the way not empty works is it again uses a for loop. Most of these will use for loops. And it'll loop not to 10, but to array.length. Okay? What it will check is if the array at spot I, okay, is not equal to integer dot min value, I will return true. So in other words, if there's something in that array that's not one of those min values, then there's something still in that array. If it's full of min values, then it's essentially all empty. So at the very end, at the end of this for loop, after the end of it, at that point, I can return false. Okay? So I have two return statements, one at the inside the loop and one at the end after the loop, to determine whether or not this array is empty or not. It's kind of a weird logic. The not empty is kind of a strange way to write it. So some of you might have to just take my word on this one. Okay. This is the next method is called find lowest and remove. This is actually the longest of the methods so far. But am I going too quickly? Has anyone not got that yet? Okay, taking a sip of coffee and then we'll go to the next one. Okay, find lowest and remove. This is essentially a search to find the lowest value. So I'm going to start by making something called lowest. And I'm going to make it equal to integer dot min value. Sorry, max value. So I'm going to start the lowest off at an extremely high number. I'm going to create a variable called location equal to -1. That's where I'm going to find it. I'm going to start my for loop going. I'm going to go through to the array.length. And my caps lock is on. Okay. And now I'm going to determine if the array at spot I is less than the lowest, but I have to also have one other condition with this. And, remember the and symbol, and array spot I. And I'm going to move this down a line just so I don't run out of space there. And array.I is not equal to integer.min value. Because that one is going to be an extremely small number, but it's one we want to ignore. We want to ignore that because that's representing a deleted value. So that min value represents something that's deleted, so that's why we're skipping it with our if statement. But if that's true, then the lowest number equals array spot I. That's now the lowest number. And the location is equal to I. That's the location I found it at. Oops. Okay, so that loop will go through the array looking for the lowest value, and it'll track its location as it goes through the array. At the end, after the loop is done, I will go into the array at spot location, and I will delete it by setting it to integer dot min value. Remember, that represents a deleted spot. There's actually a name for this, which I'm going to go over in a minute. And then the last thing I do is I return the lowest. I have to return that. What we're doing here is we're not really deleting the spots. We're just setting them to that extremely small number. This process, you guys are going to love this as teenagers. This process is known as lazy deletion. Because you're not actually deleting it from the array. We're not actually resizing the array. We're just tracking it and marking it as deleted by setting it to an extremely rare value. This is called lazy deletion, and it's not the most efficient code, but it works, just like duct tape. Okay. I'm going to try and beat the buzzer here, kids. Add to back. The rest of the methods aren't as long. That was the longest one, find lowest and remove. Add to back. What this method's going to do is it's going to put that variable lowest at the back of this array. Well, and by back I mean the first spot that's not empty. So here's how it works. I fire up a for loop again. Going through duplicate.length. This time it's called duplicate because that's the name of the array we passed it. We passed it duplicate. Okay? I say if duplicate spot I equals integer dot min value. That's an empty spot. That's the empty spot I can use. So if I just found an empty spot, duplicate spot I equals the lowest. I put it right there. That's where I can stick it, right there. And at that point, I can just return. I'm done. I don't need to keep looping. I can just get out of there at this point. I'm done. So that's how I'm going to add it to the back of that array. It's really adding it to the first available spot that I can use. And then finally, we have to make a copy. We have to copy the duplicate onto the array. Now I'm going to rename these two parameters right here. I'm going to rename duplicate source, and I'm going to rename array target. That'll make a little more sense. I'm copying the source onto the target. And all I do for that is use a for loop, going through source.length, and I say target spot I equals source spot I. That's it. That's how I copy it. And you'll actually get a light bulb here, because built into Java is a way to already copy one array onto another. And if you want, you could use that method. But I just think it's useful to write your own method for that. But hopefully now, with all that code in place, I'm going to run the test on the selection sort algorithm, and it hopefully should work. Okay? Oh, am I still at that huge number? 15,000, I guess I am. Okay? So here you can see it just built, and there it did. 9 seconds. It did the second sort, the selection sort algorithm. Okay? So just to distinguish them, I'm going to put the word selection sort here, and I'm going to put the word bubble sorted here, so that, again, you can kind of see what's going on there. Okay, we're going to stop there for today. Okay, so here's where we're at now with this searching and sorting example. We created the structures, okay? We created a random array and a random item to look for. We did the first, which is the linear search, the most simple of the search algorithms. So it's searching a random array for a random item. Then we re-randomized the array and did the bubble sort algorithm. And the bubble sort is the simplest of the sort algorithms, though it's not the most efficient. Okay? And it's certainly not the most intuitive. Then we re-randomized the array and did the selection sort. Now the selection sort is actually the more intuitive algorithm. It's the way you would probably do it naturally. But the way we wrote the selection sort algorithm, if we take a look at the last thing we wrote last week, this selection sort algorithm makes use of a few other methods. The create empty duplicate method, etc. So I'm just going to collapse those. So the selection sort algorithm uses 5 other methods to implement. But that's not the only way you can write the selection sort algorithm. So what I want you grade 12s to do right now is go in and I want you to write a second selection sort algorithm inside the sort tools class. Now, this will not be overloading because it's going to have the same parameter. So we're going to have to call it something other than just selection sort. So let's call it selection sort optimal, because this is a better version of selection sort, and it takes an integer array as a parameter. Okay? So this is a second version of the selection sort algorithm, but this one will be different than the previous one. And how it will be different is it doesn't call any other methods. So this one, all the logic resides just within the method itself. Okay? In order to do that, it has to be a little more complex. The previous selection sort algorithm, if I just open that one up, is fairly intuitive, although it calls on other methods. It creates a duplicate, an empty duplicate. While the array's not empty, it finds the lowest and removes it from the original array. It adds the lowest to the back of the duplicate array, and then it copies the duplicate onto the original array. It is fairly intuitive in its design, but it makes use of lots of method calls. So in reality, it's actually not that efficient in terms of memory usage or speed. So our selection sort optimal is going to work a little bit different and a little bit more efficiently. Okay. So here's how this selection sort optimal is coded. Let's move that down. It starts with a for loop. Okay? The for loop goes through array.length, but array.length minus 1. So it goes to the second last item in the array. It creates a lowest value equal to I. So lowest will be 0, 1, 2, 3, all the way through the array. So lowest will be set to the I value. Then it starts the second for loop. And this one goes through array.length. Okay, so now the second for loop is using the j variable to loop through array.length. And inside here, we hit an if statement. If the array at spot j is less than the array at spot j, or sorry, at spot array lowest, then lowest equals j. So this performs a swap like we did in the bubble sort, kind of, but it's not really swapping each one. It's checking to see if the array at spot j is less than the array at spot lowest. Okay? And then finally, it hits an if statement. If lowest, oops, is not equal to I, here we actually have to perform the swap algorithm again. Int temp equals array spot I, array spot I equals array spot lowest. And then finally, oops, array spot lowest equals temp. So this performs a swap. So in a lot of ways, it looks very similar to the bubble sort algorithm in the sense that we're performing a swap at this point. But the logic here is slightly different. Now, there's one other thing that we have to change. Because at this point, it looks so much like the bubble sort algorithm. And the change happens up here. J does not start at 0. J starts at I plus 1. That is an important change to make, okay? You can even put it in brackets if you want, just to sort of keep it together, okay? So that's an important change right there in the algorithm. Now, as I said before, this is a more efficient algorithm, but it's a little bit harder to follow just by looking at the algorithm itself. But before we get too deep into it, let's test it. So let's go back to here, and I'm just going to copy and paste the selection sort code, and I'm just going to call it selection sort optimal, and that's the one I'm going to call selection sort optimal. So this time when I run it, it should selection sort again, but it's using the second algorithm to do this. Not the first algorithm. Well, it's using both. It does the first one and then the second one. Okay, and it is working. It's putting it in, and I'm just going to call this selection optimal. Okay. And it is working. You can see here on the very last line, it's putting it in order from lowest to highest. Okay, so let's take a second to analyze how this algorithm actually works. Okay, so it's a trickier one to follow. And by the way, this is the kind of thing you'll encounter a lot in, say, university computer science exams, is they love to give tricky algorithms and hope you can trace them. So here's the thing. We start with an array. So I'm going to draw out the array, not make it too big. Spot 0, 1, 2, 3, 4. This is called array. Let's fill it up with random numbers. 5, 7, -2, 20, 6. Okay? So here we go. We start with a variable I. And I starts at 0. The length of this array is 5. So we know it's going to go to that, but it's going to go to 5 minus 1. So it's going to go 0 to 4. It then makes a variable called lowest, and it makes it equal to I. So it's also 0. Then it makes a variable called j. Oops. And j is equal to I plus 1. So j becomes 1. And it will loop up to the length. So it'll loop up to 5. Well, 1 less than 5. Okay? It says, is the array at spot j, spot 1, less than the array at spot lowest? So is this less than that? No. So it skips that. But then it increases j by 1. So j now goes to 2. And 2 is less than 5. Okay? So is spot 2 less than array lowest? In other words, this spot. So now it's comparing spot 2 to the very first spot. And it is lowest, right? Negative 2 is lower than 5. So now it says lowest equals j. So now lowest becomes 2, not 0 anymore. Okay? And then it continues. Now j goes up to 3. Is array spot 3 less than this one? No. So then lowest goes to 4. Is array spot 4 less than array spot lowest? No. So you can see what this inner loop has done is it has found the lowest number. It's at spot 2. So what this inner loop does right here is essentially what our other algorithm did was it finds the lowest. But then here's what it does with the lowest. It swaps the lowest with the spot we're currently at. And we're currently at spot I, which is spot 0. So now what it does is it swaps the negative 2 to here and the 5 to here. So then it goes back and does it again. So that finds the lowest, and this part of the algorithm swaps it with the current spot. And the current spot will keep moving through the array, and it'll go all the way up to the second last one, performing that swap as it moves. So in a way, it is definitely more efficient by doing that. But when you just look at this algorithm without kind of clearly knowing that, it's harder to grasp. Whereas this one, I think, is easier to grasp when you first look at a selection sort algorithm. But it makes use of lots of other methods, so you had to do a lot more work to get it going. Whereas this one, all the logic is contained within the algorithm itself. Okay, so now you have two versions of the selection sort algorithm. We really kind of had two versions of the bubble sort algorithm as well, although we didn't write both of them. Remember, the very first time we wrote bubble sort, it was a very simple version of bubble sort that did not use the Booleans and all that. So this is already the optimal version of bubble sort. So in theory, you could get rid of the old selection sort for the new one, but I think it's still good an exercise to leave it there. Okay, so now I want to teach you your second search algorithm. We now have two sort algorithms. So now I want to teach you what's called the binary search algorithm. Okay, so to do a binary search, we need an item to search for. So I'm going to redo this line up here. I'm going to get a random item to search for. So that'll look for it. Okay. I will also randomize the array. So I'm going to take that line from up top there and re-randomize the array. Okay? Actually, I won't. I'll skip a step. The only way binary search works is if the array is already sorted. And it just so happens that it is, because we just sorted it with the selection sort algorithm. So I'm not going to re-randomize it. I'm just going to use it in its current state, which is a sorted array. Okay? So now I've got an item. So now I'm going to do these two lines, which I'm stealing up here from linear search. But I'll just put it here. This is a binary search. And that's what I'm going to call. I'm going to call the binary search, which doesn't exist yet. Okay? So here's how I'm going to implement the binary search. I'm going to look for an item. I'm going to create an item to look for. I'm then going to call on the search tools method class and use a method called binary search. And then I will display the results for the binary search for this item at this location. And we've already got code that'll take care of that in our show results method. So really all we're going to focus on is writing this method called binary search. Okay, so everyone take a second to get that in. And now we're going to go to the search tools class and write this method. Didn't write it. There we go. Create method binary search. There we go. Okay, so we're now in the search tools class. And we're going to write this method called binary search. Now here's the way binary search works. Okay, I'll just describe it to you. It's a fairly simple algorithm in terms of describing it, but it's a little more complicated in terms of how to write it. Okay, so what you have to start is you have an array, obviously, which, by the way, does not have to be the only structure that can store things to be searched, but it's the only structure that you're kind of very comfortable with at this point. And the nature of the binary search is it has to search through an array that has already been sorted, which is the case that we have. So I'm going to put some numbers, but they are going to be in ascending order. -6, -1, 0, 2, 4, 40, 100. So that's a sorted list. It's going from low to high. The way binary search works is this. Let's say I'm searching for the item 4, which happens, we know, to be in this list. Okay? The way it works is because it's in sorted order, it starts by looking for 4, not at the beginning of the list, but in the middle of the list. So this is a list of 7 items. So the middle of this list is here. This is the middle. And it says, is this thing 4? No, it's not 4. But what we do know is, I no longer have to search in this whole half of the list. That whole half of the list, because it is less than 4, I don't have to worry about it anymore. Now I've reduced my search area to half the size. Now I take this half of the list and I cut it in half again. I search the middle of it, which would probably be around here. Is that the 4? No. But now I know this whole half of the list I don't have to worry about because it's greater than the number I'm looking for. And now I can do it again, and sure enough, I'm going to find it. And that only took 1, 2, 3 checks to work, versus the linear search, which would have went 1, 2, 3, 4 checks. And again, this is a very small list. The binary search is extremely efficient because it halves the amount of things to look through every single time it looks. And here's how it's implemented. Okay. So to write this method, we need to keep track of 2 points in our list. The high value, so we're going to make an integer called high, and it's equal to array.length minus 1. That's the high value. The low value as well, it's equal to 0. That's the high and low of any array, because it's essentially the 2 points that we're going to separate the list by. So all arrays we know start at spot 0. All arrays will end at spot length minus 1. So we keep these 2 markers, high and low. We then implement a while loop. While low is less than or equal to high. So in other words, what's going to happen is these 2 markers on either side of the array are going to keep moving. But if they collapse on themselves, in other words, if they become the same number or they somehow pass each other, then what that means is we can't find it. So at the bottom of this loop, after the loop is finished, that's where we return -1 that we did not find it. Okay? Inside the loop, what we have to do is calculate the middle point, which I'm just going to call mid. And mid is a calculation that looks like this. It's high plus low divided by 2. That's how you calculate the middle of it. You cut the list in half. You add the high and the low together, and you half it. And then we just have a series of if statements, 3 of them. If the array at spot mid equals my item, well, then I found it. So I'll return mid. I'm done. Now I'm just going to shorten up the if statement by keeping it all on one line because it's so simple. Then I go else if the, and I'm going to slide that over so that it all lines up nice. Array at spot mid is greater than my item. Okay, well, if that's the case, then I don't need to return, but what I have to adjust is my high value. My high value equals my mid minus 1. I shift the high value over. And then the final part of this algorithm is else if the array at spot mid is less than my item, then it's the low that I change. My low equals my mid plus 1. And that's it. That's the whole algorithm. It is extremely short and simple. It's one of the most beautiful, like, if you think of code as beautiful, but it's just a simple, clean piece of logic that will work. And it's incredibly efficient. So I'm just going to show you how this would work now. I'm just going to run that code. And it's saying right there that item -7 was found at location 2, 0, 1, 2. Look at that. It worked. It found it, and it's extremely efficient in terms of how it does that. Now I'm going to run it one more time. Let's see if it works with a not found. Item 0 is found at location 6, so it found it there. Running it again. Item -12 was not found. And you can see there is no -12 in that list. So that worked really, really nicely. Okay? Now I just want to trace this algorithm again with you guys just real quick to show you how this is working. Okay? Because I described it to you. So let's do it one more time. I'm just going to draw out an array. Okay, so this is an array of 8 items. Okay? -5, -2, -1, 0, 2, 6, 40, 100. Okay. So let's say I'm searching for the item 2. 2 is the item I'm searching for. Okay, so it makes 2 variables. It makes a high variable and a low variable. And it will also, in the middle of this algorithm, calculate a midpoint. Okay? So we have high, low, and mid. That's it. Those are the only variables in play here. 3 simple integers. High is equal to length, which is 8, minus 1. So high will be 7. Low is 0. While low is less than high, well, yeah, 0 is less than 7. The mid is this plus this, so 7, divided by 2. Now we're dealing with integers. So when you divide 7 by 2, the answer is 3.5, but integers can't do 0.5. So it always truncates it to 3. It never rounds it off, it truncates it. So the answer is going to be 3 there. Okay? So it's going to start with this being the low, this being the high, and this being the mid. And it checks. Is the array at spot mid equal to my item? No. Is the array at spot mid greater than my item? No. Is it less than my item? Yes, it's less. 0 is less than 2. So now what it does is it takes the low, and it makes low into mid, which is 3, plus 1. So low becomes 4. Okay? See how it worked there? And then it goes back up the loop. Is low less than high? Yeah, 4 is less than 7. So it recalculates the midpoints. The mid is 7 plus 4, which is what? 11. 11 divided by 2 is 5. So now this is the midpoint. This is now the low point. That's no longer the mid. So the mid is now 5. Okay? And now you see what happened. It shot past the 2, but that's okay. It's going to adjust to this. It says, is the array at spot mid equal to the item? No. Is the array at spot mid greater than the item? Yes, it is. 6 is greater than 2. So now the high becomes the mid minus 1. So it takes 5, subtracts 1, and it makes the high into, sorry, not 6, into 4, right? So this is no longer 0, it's 4. And it goes back up the loop, and now it's going to recalculate the mid. So the mid is high plus low, 8, divided by 2, 4. So now the mid is 4. So now this is the mid. And now it hits the if statement. Is the array at spot mid equal to the item? Yes, it is. Return the mid. So it returns that it found the item at spot 4. So that's how the binary search works. It keeps collapsing the list down till it finds the spot, or if it continually collapses down, these two numbers will eventually become past each other, right? So it keeps looping while it's less than or equal to high. Right now they're equal, so it kept going. But if that number got too small, the list would collapse in on itself. Because think about it, right? Low would have been recalculated and stuff like that, so it keeps shifting the values around, okay? It is an incredibly efficient algorithm. But we can actually write this algorithm one other way, and that's what we're going to do next. We're going to write a second version, a public static int binary search optimal with the integer array. So we're going to write this algorithm one more time. And it's almost identical to the one above with a slight difference. Okay? It has one line. We return recursive binary search. In the whoops, I forgot the item. Int item. For the item in the array. And we need two more parameters, 0 and array.length minus 1. Okay, so let me zoom in on that so you guys can see what I've been doing there. Okay, so this is going to make a call to another method that we're going to write that's recursive. So the whole idea here was, what I wanted to show you about the binary search is it can be done recursively. So it's a throwback to our first unit. So we don't know that when we just call binary search optimal. When we call binary search optimal, we're just searching for an item in an array. But hidden within that is a recursive method. And recursion is often done that way. Recursion is hidden within a class using what's called, this is actually called a wrapper method. Doesn't mean it like, goes out with Rihanna or anything like that. It just means that this method is hiding the fact that recursion is taking place. The reason we're going to then also send two other parameters are because of the way the recursion works. Okay? Now this is an extremely small method. Like any recursive method, it's going to be very simple to write. But let's do this. It will be a private method. Okay? So recursive search binary, a recursive binary search. And we're going to rename the two parameters instead of I and I0 as low and high. Okay? So recursive binary search will take the item, the array, a low, and a high variable. And here's how it's coded. It's like 5 lines. If low is less than or equal to high, hit this if statement. Otherwise, return -1. It's not found. Okay, so it starts with an if statement. If low is less than or equal to high, do something. It calculates the midpoint, like it did in the previous algorithm, but this time I'm going to use a slightly more efficient calculation of midpoint. The one I previously showed you actually has a potential for a once in a very rare case, but there is an error possibility. And it was actually one of my former students who's now a master's student at the U of M studying searching and sorting in a master's thesis that told me, no, this is the better way to write it. And so I am listening to current research. Plus high minus low divided by 2. So this, believe it or not, is actually a more efficient calculation of the midpoint. High plus bracket high minus low divided by 2. And then we hit our if statement. If the array at spot mid is greater than the item, I return recursive binary search for the, okay, let me pull back here a bit. Okay, so this is where the recursion takes place. But what I do here is instead of putting high right there, I put mid -1. Okay? And I'm actually going to move that down a line just so it shows like that, just for space efficiency. Else if the array at spot mid is less than the item, I return recursive binary search for the item in the array, but this time the variable I change is low. Low becomes mid +1. And then finally I just have the else. I return the mid. And that is it. That is the entire recursive binary search algorithm. It uses a similar logic to the previous one, but by doing it recursively, it actually is even more efficient. Now, I'm not going to trace this one with you guys. It is a bit complicated to trace, but it is incredible to look at sort of the efficiency of this. Now I'm going to just move these up just to save space. Because that's it. That's the whole algorithm right there. As simple as it is. Okay? It's just that many few lines of code to actually get working. Okay? But you can compare these two, and again, this is some pretty high-end coding here. This is often looked at second-year university level computer science courses. The efficiency of search algorithms, and I'm glad to share that with you guys. But we should test it. We didn't test this recursive binary search. So I'm going to run all this binary search code again, but this will be binary search optimal, and that's the one I'll call binary search optimal. Okay? And run that code. Yep. So it says -10 was found at location 1, and there it is, right at spot 1. And that's binary optimal. Okay, so here's what we know now. In our sort tools class, we have 3 sort algorithms. The bubble sort, the selection sort, and an optimal version of the selection sort algorithm. In our search tools class, we have as well 3 algorithms. A linear search, and a binary search, and a more optimal version of the binary search. So really we have 2 sorts and 2 searches, but we have a more optimized version of the second sort and the second search. We also have a few private methods The search tools class has a recursive private method, which is hidden by its wrapper method. The sort tools class has a few utility private methods that are used by the selection sort algorithm to just make it work and make the logic broken up a bit more. Okay? We ran all of this through a driver program that drives all our code to test it all in main that runs the linear, the selection, the binary, etc. Okay? And that's where this example ends. So that's the two sorts and the two searches that I wanted you guys to get out of this. And that will be worth points if you turn in your example right now as is. For extra points, I'm now also going to write a few other searching and sorting algorithms tomorrow that are optional. You don't have to do them, okay? If you want to, you can. I'm going to record those so that those are on the video as well. But there's a few other algorithms that are just a few more sorts and searches. Include some that are pretty, a little more advanced. But I just want to finish up a little piece of the presentation that goes over this just with you guys, just to wrap today. So this is in the notes on the binary search. Okay, so the caveat with the binary search is, as I said, it only works on a sorted list, okay, using a divide and conquer technique, okay? By examining the middle of the list, if the item is the one you're looking for, you're done. And then whether it's low or high, it will adjust the search criteria until it finds the item or until low or high collapse on each other, which means that the item's not in the list, okay? So in the code, I have examples of this in play that I did on the projector as well. So it can start in the middle and it can keep dividing the list in half and in half. It is extremely efficient. Here's some stats for you. In an array of 100 elements, if they have an array of 100 different values, it would take no more than 8 possible checks to find it. Now think of that compared to the linear search. What would be the worst case scenario in the linear search would be 100 checks. So this is significantly more efficient. But wait, let me up this again. If we had 1 million elements to look through, it would take no more than 20 checks to find the item we're looking for. Versus the linear search, which would be 1 million checks. Now, let me take it one step higher. If we had to search the entire world's population, no more than 40 checks would have to be done using the binary search. This is a lot more efficient. But what was the initial criteria that makes it a little bit tricky? Is that it has to be sorted. So although the binary search is an extremely efficient algorithm, it relies on the list being already sorted, okay? The code's in the notes. You can see it there, okay? It also has the example of the recursive binary search in the notes as well, okay? So there's all kinds of stuff in play here, right? Like in terms of efficiency. Efficiency of an algorithm for sure deals with speed, but it could also deal with things like preconditions, like that it has to be sorted, or space, that certain algorithms take up or use more space. Okay, and we'll wrap that for today. Okay, so here comes the extra search sort algorithms that I said we'd be doing today. So we're going to start with one called the insertion sort algorithm. Okay, so like the other ones, this is a sort algorithm. So I'm going to steal a little bit of the code from up here, from any of the other sorts, and place it down here. And this time I'm going to be doing the insertion, not optimal, the insertion sort algorithm. And that's the name of the method I'm going to make, called insertion sort. Okay? Okay, so this is another algorithm we're going to put into our sort tools class called the insertion sort. So it's going to sort the array as well. So we start by scrambling the array, by recreating it. We display it in its scrambled state. We then run the insertion sort algorithm and display it sorted afterwards. Okay? So again, you don't have to type all that code. You can just copy and paste it from up here and just change a couple things with it. Okay, this is not a long algorithm, but it's got, again, some tricky logic that you got to kind of follow. I think it's only about 7 or 8 lines long. It's not that much lines of code, but it's a little bit tricky to grasp. Okay, so let's write this algorithm. Create method insertion sort. Okay, so this will be made inside the sort tools class. You should now be able to find, it should have built a method in there called insertion sort. And there it is. Okay, I'm going to put the modifier public at the front. And let's get coding. Okay, like most sort algorithms, this incorporates a loop. Okay, so we're going to have an I loop that goes to array.length. Okay, so we go from 0 to array.length, but here's the first change we make. This loop doesn't start at spot 0. It starts at spot 1. So that is a major change from a lot of our algorithms, is it doesn't start at the first spot, it starts at the second spot. Okay, so I'll sort of leave that for now. You'll kind of grasp that later. Okay, now we make another variable, j, equal to I. So we have a second variable that's equal to I. So it's also going to be 1 at this point. We now need to hang on to a temporary value, very much like the swap algorithms. We get it from array spot I. Okay. Now remember, that's spot 1 at this point. Now, here's where it gets weird. Instead of using a for loop, we now use a while loop. While j is greater than 0, and I'm going to put that as its own condition inside its own set of brackets. So while j is greater than 0, and array spot j minus 1 is greater than temp. Okay, so it's a tricky piece of logic there to kind of grasp. We'll go through it in a minute. But make sure you code that correctly, okay? Make sure your greater than signs and less than signs are in the correct spots. Make sure it's j minus 1, not j minus I. Make sure it's j is greater than 0 and greater than temp. Okay, 3 more lines and we're done. Array, this is inside the loop. Array spot j equals array spot j plus 1. And then j minus minus. J is actually going to go down. And then finally, one last line after the while loop. Array spot j equals temp. Okay, before I explain this algorithm to you, let's make sure it works. Okay, so that's the algorithm. I'm just going to run my code. I know some of you guys are still typing. But you can see it didn't work. So I've made a logic error. What it's done is it's made negative 13, negative 13, negative 11. So embarrassing as I'm... Oh, here's the error. So silly. That should be a minus sign. My apologies. Wow, let's just make sure it works this time. Yep, now it's fixed. So that's what you can see, that this kind of algorithm is really, really temperamental. Okay, so let me draw a real simple array and try and run this logic. Okay? Okay, and I'll just scramble it up. So 5, -2, 0, 100, -1. Okay. So here's how it works. It starts with a variable I, and I is a 1. And I is going to keep going while it's less than the length of the array. And this array has a length of 5. That's the length of this array. It then makes a variable j, and it's equal to I, so it's 1. It then, I'll put this one over here, makes a variable temp, and it's equal to the array at spot I. So at spot I is the value -2. Okay, here comes the tough logic. While j is greater than 0, well, 1 is greater than 0, so it meets the first condition. This has to be true, and this has to be true. The array spot j minus 1, well, j minus 1 is the spot before that. So is j minus 1 greater than temp? Yes, it is. This value is greater than temp. So both conditions are true, so it enters the while loop. And it says array spot j, which is that -2, equals array spot j minus 1. So this becomes 5, and now j goes down. J goes down to 0. Now it attempts to run the loop again. Is j greater than 0? No. So it fails the first condition. So because that's an and, there's no need to even check this second condition. And means both have to be true, so it leaves the while loop. And then it says array spot j, which is a 0, equals temp. So now the -2 goes here. So it looks like I've just performed a swap, but we're still not done yet. So now it comes back up inside the for loop. I goes up by 1. So now I is 2. Okay? J is now equal to I. So it's 2. Temp is equal to array spot I. So temp is now 0. Okay? Now while j is greater than 0, that's met. And array spot j minus 1, that's the 5, is greater than temp. Well, 5 is greater than temp, so it enters the while loop. Array spot j, array spot 2, equals array spot j minus 1. So this becomes a 5. J goes down by 1. Now we're at 1. Now, it meets this condition. It's still greater than 0. But as array spot j minus 1, well, j minus 1 is spot 0, which is the -2. Is that thing greater than temp? No. -2 is not greater than temp. So it leaves the while loop. Array spot j, array spot 1, is equal to temp. So the 0 goes there. So at this point, it kind of looks like it's performing the bubble sort algorithm, but it's not. Okay? This algorithm is more efficient. I'm not going to go through the rest of it with you. But in the end, what it does is it performs less operations to sort that. And that's the insertion sort algorithm. Okay? It's not that commonly written because it is a bit of a sort of a mysterious algorithm, but it works. Okay. That's insertion sort. Now we're going to write another one. This one's also optional, and this one is called the shell sort. And where do you think this one comes from? Any idea? Where would the word shell come from in a sorting algorithm? This would be for any of you guys who've been to carnivals, maybe. You guys ever seen those guys at carnivals that have like 3 shells and they put a ball under one of them and they start mixing them around and you have to guess which one the ball's under? Don't ever play that game. They're professionals. They're going to totally take your money. But that's what that is. That's the sort of thing that's going on there. Is the shell sort is a kind of a swapping algorithm as well. Okay? Very much like the insertion sort, it's just got some tricky logic. It's about as long as the insertion sort. Okay? So now we're going to create this thing called the shell sort. So let's go do it. Okay, and we'll make it a public shell sort. Okay, this one starts off by making an integer variable called j equal to 0. Okay. Then it uses a for loop, but I'm not going to automate this one because it's a weird. Int gap equals array.length divided by 2. Okay, so that's a strange start to this for loop. It creates a variable called gap that starts at the midpoint of the array, because I divide it in half. While gap is greater than 0, here's again the weird logic, gap equals gap divided by 2. So it cuts the gap in half. So it keeps dividing it by 2 each time through the loop. So a very, very strange for loop there, using a variable called gap. Now we have another for loop. This one I'll finally use I. If I, for int I equals gap, well, I is less than array.length, I plus plus. So that's a more traditional looking for loop, but it starts at the value gap, which is this weird calculated value. So really what gap is doing is it's going halfway, kind of, through the list. Okay, inside this for loop, we make a temporary variable, temp, equal to array spot I. And then, believe it or not, we have another for loop, for. But here's where it's weird. Here's where we finally use j. For j, and we don't have to say int j, because we did that up here. We made j. For j equals I, inner bracket, j is greater than or equal to gap, and temp is less than array, spot j minus gap, semicolon, shrinking that, j equals j, oh, what happened there? Oh. J equals j minus gap. Okay, so nasty, nasty logic here at this point. Okay, not going to lie. And then one line inside that for loop, array spot j equals array spot j minus gap. And then finally after that for loop, last line, array spot j equals temp. Okay, I don't think I'm going to go through this algorithm with you guys. I just want to run it to just make sure it actually works. Shell sort, and it does. Okay. So believe it when I say to you guys, I did present to you some of the easier sorting algorithms. You can see the amount of mathematical formulation that went into this one, okay, is intense. Okay, it's got an intense amount of sort of for loop action going in there. Here's an extremely fancy word for you guys. Cyclomatic complexity. Oh yeah, I sound smart when I say that. Cyclomatic complexity refers to how many different ways a method can return. And it has a few more things that are part of it. This is not a return method. It's a void method. Okay? So its cyclomatic complexity is actually 0. It has, well, it's 1. It has one way to return when this method's done. Versus the example I just did with the grade 11s, some of those methods had a cyclomatic complexity of like 2 because there were 2 different ways it could return. But what actually is going on inside this algorithm is a lot of complex mathematics there based on a lot of these formulas. Okay? But something to think about. All right, how we doing? We got a little bit of time. Let's start this the very last optional algorithm. And it's called the quick sort. Okay? Now, one thing real quick, I just want to go back to that example, that animation I showed you guys yesterday. So at this point, you should be at least running your code to make sure that it is performing all these sorts. So the insertion sort is sorting it, and that the shell sort is sorting it. And again, when you take a look at this now, when you take a look at your actual class, you have a lot of really nice methods now for sorting and searching your code. Whoops. Just going to collapse them all. So we have the bubble sort, the selection sort optimal, the insertion sort, and the shell sort. You have all of those to choose from. These are all little private methods that are used inside there, but right, those are all some sort methods that you can use. You similarly had some simple search ones. So now, using that example, Java sorting animation from this website, okay, you have a lot of these. You have the shell sort, you have the insertion sort, selection, bubble. Okay, I don't have time to do the merge or the heap, but I'm going to do this one, the quick sort, not quick 3, but quick. And now again, as you look at these algorithms in action, now you have this algorithm, the sort, and look how fast that one did there or down here. It's beating the bubble sort on a lot of these things. Okay? You also have the shell sort, which is already done. So I wish this went a little bit slower so we could kind of feel, but here you can see the shell sort working away. It's done this one, this one, this one, whereas selection and bubble are still working, and even insertion is still working. So that shell sort, the last one we just wrote, is faster so far than the other ones. So I'm getting a good speed out of it, even though it's got a complex logic to it, it's got good speed. Okay? So now we'll just start this one today because we won't have time before the bell. But we're going to do one more called the quick sort. Okay? And the quick sort is a recursive algorithm. Okay? All the more why you need to kind of learn recursion before you can do quicksort. Okay? So we'll just set it up for tomorrow. I'll create the method quicksort. And by tomorrow, I mean Thursday, because I'm on a field trip tomorrow. And that will be on Thursday's agenda, is we will write the quicksort algorithm for use, okay, in this program. And that will give you guys some bonus points, those who want to try it. And again, especially any of you who are going to plan on taking computer science at university, it's good to have a warehouse of these libraries ready. I know you can get them online, right? Even at this website, I think if you click on shell, it shows you the algorithm right here. Although it's often in other programming languages or it's in pseudocode like this. I don't know if you can actually get the Java version of it on this website. Okay, so you might have to, Google it. And sometimes the web is just too large of an information source. Okay, so if I want a Java shell sort algorithm, Stack Overflow, a great example of that for sure. You can get some of this code pulled in. But now when you go and compare it to the code that we just wrote, so there's that shell sort, will it be easier to interpret, right? A lot of times people will try to show off their coding. So here is a snippet of code right here. Okay? And here's their version of shell sort right there. Is that easier? I don't know. You'd have to look at it to kind of get a feel for that. Maybe it is. Keeping rolling down this article, oh, this guy says this is a simpler version of shell sort. Okay? This one looks very similar to mine. It's using a variable gap and stuff like that. Okay? However, this uses what's called a comparable interface, which you guys don't know about. So that might leave you a little bit lost at this point. Okay? Similar with this one, a little bit more complex. Okay? This one is similar to the one I wrote with you guys, but again, maybe not quite there. Now here's one that uses an integer array, just like we did. So that one might be better. But you can see here, it uses a series of while loops to implement the algorithm, rather than a for loop. Maybe that one's an easier version. I don't know. It's certainly more lines than the one I wrote with you guys, but maybe it's easier to interpret. Only you can be the judge of that. Okay, so last time we just ended by introducing this idea that we're now going to do the quick sort algorithm. So this was the last piece of code we put in, that it's going to re-randomize the array, display the array, perform the quick sort algorithm, and then display it after the quick sort. Now I'm just going to run the code real quick. So I made a few adjustments to the display method. If you're interested in seeing that, it doesn't matter. I just wanted to do it so it looks nicer. So here are the things we did: the new array, the linear search, the new array again, the bubble sort, the new array again. Every time you call new array, it just re-scrambles it. Selection sort, the better selection sort, the binary search and the optimal binary search, the new array, the insertion sort, the shell sort, and now we haven't implemented it yet, but the quick sort, how the quick sort will sort this array of integers using its algorithm. Okay? So to implement the quick sort, we're going to do this recursively. Okay? So I want to just present a little bit of theory behind this. This is in an optional section of my notes on the quick sort algorithm. And then we'll just quickly code it. I'm just going to go through this real quick. Okay? So if you think about an array of items, okay, and you pick within that array of items what's called a pivot point, okay, which does not, by the way, have to be the middle point. But if you pick a pivot point, you can set an array of a certain way. So let's imagine we had a collection of random numbers just in front of me right now, like a bunch of dinner plates with numbers on them. And they were in a line, but they were not sorted. And I just pick one spot in the line and I go, you know what, here's what I'm going to do. All plates that are less than my spot, I'm going to toss over here. And all plates that are greater than mine, I'm going to toss over there. That will separate the array, but the pile that I make over there is not sorted. And the pile I make over here is not sorted. It just is such it's true that from the pivot point, all items will be greater or less than that pivot based on the spot you pick the pivot. Okay? Seems like a simple enough concept, and it is. Okay? This will separate the array into two subarrays. I'm going to call them S1 and S2. The front of the array, F, and the back of the array, B, is true mathematically such that S1 is from A front pivot index minus 1 less than pivot index, which is greater than S2, which is A, the pivot index, plus 1 all the way up to B. Don't worry about that. That's just essentially a mathematical way to describe it. Okay? But then all I have to do is reapply that logic to each subarray. So within the subarray, I can perform the same logic. I can go pick a pivot point, throw everything on one side, throw everything on the other. Then do that here. And if I keep doing that recursively, it will end up with a sorted array. And that's essentially what it does. Here's the pseudocode for it. To quick sort an array, I partition the array into two parts, then quick sort each part. That's how simple it is. The real logic goes into that sub-method to partition the array. Okay? And then it performs a recursive quick sort. Okay? So anyways, this is more of pseudocode, but let's actually put this into real code. Okay, so to quick sort the array, I'm going to call recursive quick sort of the array, comma, from position 0 to the end of the array, which we can define as array.length minus 1. So this recursive algorithm needs to know what array I'm sorting and from what spot to what spot. So because it's the first call, I'm going to sort the entire array from 0 to the end. So now I'm going to build this recursive method, recursive quicksort. Okay? And I'm going to rename these two variables, instead of I and I0, as simply the front and the back of the array. Okay? So you may recall this is what's called a wrapper method. It hides the fact that recursion is taking place because this method is private. This is the public method, quicksort, that the users see outside the class. This is the private method within the class that hides the fact that recursion is taking place. Okay, this is a recursive method, so it will be short. Basically, it looks like this. If the back is less than or equal to the front, well, then I'm done. I'll just return at this point. This is, for what you may recall from our unit on recursion, this is what's called a base case, right? This is what stops the recursion from taking place. Basically, that means that the array has now been shrunk to such a small size that it's basically size 1. So there's nothing to sort on an array that's of size 1. The back and the front are the same number. Or somehow they've passed each other. That's more of an error check. But really it should be if back equals front, which means I kept dividing the array into smaller chunks until now it's just one chunk. Well, there's no need to do any logic on a one chunk array. You just return. But the else is now the recursive case. Okay? The recursive case is based on a pivot value. Okay? We're going to get the pivot value from a method we're going to call partition. Whoops. And we're going to partition the array from front to back. Okay? Now, we will write this method in a minute. We'll get to the partition method. That's actually where the most logic goes. But then we have two other things to do. We recursive quicksort the array from the front, but not to the back, to the pivot minus 1. That's essentially, that's subarray 1. Okay? That's S1, the subarray 1. And then we will recursive quicksort the array, but not from the front, but from pivot plus 1 to the back, which is essentially S2. And that's it. That's all recursive quicksort does. It basically cuts the array into a pivot spot and then sorts one half and then sorts the other half. That's it. All our real logic's going to go into partition. Okay? But the method itself is recursive. It has a base case and it has two recursive cases. Okay, so now we have to write this partition method. And it will partition the array from the front to the back, so that's good. All the parameters are named nicely. Okay, so we're going to start by creating a pivot. And pivot can be anywhere in the array, but we're going to start it at the array at the front. That's as good a spot as any to put it. So the front of the array will be where the pivot will start. Now we're going to shift the pivot around a little bit, okay? But that's where we'll start it. At the end of this method, we will return the front, because that will be the pivot at that point. But in between, we got some logic to do. The way this method works is uses a series of while loops to do this. Okay? So it's a little bit tricky, so I just want to make sure everyone's okay. All right, let's get started. While back is greater than front, start this while loop. Okay, so while back is greater than front, inside the while loop, we start another while loop. While back is greater than front, and the array at spot back is greater than the pivot. Okay? So this is a two-part while loop. It uses the same logic as the first one, while back is greater than front, but it adds a second condition, and the array at the back is greater than the pivot. While that's true, we execute one line of code, back minus minus. We shift the back, so to speak. Well, we actually shift it forwards. Okay? After that while loop, we hit an if statement. If the back equals the front, if they match, well, at this point, we need to break out of this loop. Okay? So that's an error catch that quickly just breaks out of our while loop, if that's the case, because we don't want to move ahead with our logic at this point, if that is true. But if it's not true, what we then do is we say array at the front equals array at the back. We essentially perform a bit of a swap there. Not really, but that's us essentially tossing something over from one side of the array to the other. And then the front moves forward. So I go front plus plus. Okay? So that's the first part of the partition, okay, is to do all of that. We will now be essentially doing it over again. So I'm just going to leave one space just to mark it on the screen. It's not necessary, but I'm just going to put it there. And I'm going to end a second while loop. While back is greater than front. And now this time we have a different second condition. The array at the front, not the back, at the front, is less than the pivot. Okay, so this inner while loop is very similar to this while loop, except the second condition is different. Here we said array back, here we say array front. Here we said greater than pivot, here we say less than pivot. And what we do inside the while loop is again the opposite. We say front plus plus. We shift the front forward. And then we have the same if statement error catch. So we use this line again. If back equals front, break. And then we say array at the front equals the pivot. Okay? So here's where the pivot actually comes into play. The pivot was not being assigned a value, or was not being used, really, other than being checked, where we got it right here from the front. So this is essentially, again, performing a bit of a swap there. And then we go back minus minus. We then shift the back over. Okay, so that is the while loop. And there's one more line of code to write. Whoops. And it's right here, right before we return. We say array at the front equals the pivot. Okay, which was the same line we just wrote. Actually, I think I may have made a mistake. Sorry. I did. This line right here, that's where that should be different. This should be array back equals array front. My apologies. I was looking at this line too early. Okay? So that's the opposite of this line up here, where he said array front equals array back. Now we're saying array back equals array front. Okay? So this is the logic. This is all the logic now. So I'm just going to put it all up on the screen at once so that you guys can look at it. The partition algorithm is a very odd swapping, sorting algorithm, but it's not a sort. The partition algorithm just throws stuff from one side of the array to the other based on a pivot point. Okay, let's see if it works now. I'm going to run that, and on our last line, the array should be quick sorted, and it was. Look at that. It was quick sorted. Now, what I showed you guys in the demo was that the quick sort algorithm should be faster than the other ones. So what I did, you guys don't have this code, but I made it a slight adjustment to the display class to add a way to add time, a timestamp, to the, oops. There we go, to the output, so that it actually puts time on there. So this might be useful. I'm just going to adjust my comments here to put the timestamp on there. I'm going to run it again, and I put an error in my code somewhere. Where did I put you, error? Did I screw up there? Did I screw up there? Did it screw up there? Where's this error? Oh, somehow I commented some comments in a bad way. There we go. So there we go. So there's the timestamps now on these. Now, that was an array of 15 items, right? So you can see it's only taking 0 seconds to do all these. It's working in the microseconds to all these, right? So here from 392 to 394, it took 2 milliseconds to build the new array, and then 1 millisecond, to, you know, et cetera, et cetera. But what if I made this a larger array, right? What if this was not 15 items, but say 25,000 items, okay? And I run that. So now you can see it's actually taking some processing time to actually build this array. So here it goes. Here's the first display. So between the time it takes to make a new array and the time it took to search it, and it had to search the entire array, worst case scenario, because it was not found, it still took under a second. Okay, but you can see here now the processing time is something you could play with a little bit more. Okay? So much larger values here and sorting. So there the selection sort was performed. So by the time, oh, there's a binary search that was performed, and then the optimal binary. See how quick those went? Here it just built the new array. Right now it's trying to perform a sort. It's done, the insertion sort. Now it's building a new array. It's done. Now it's going to perform the shell sort. It's done. Now it's building a new array. It's done. Now comes the quick sort. It's done. Okay? And here, if you want to do the math, you could actually see, is the quick sort, for example, faster than the selection sort? Let's do that one, just based on these two numbers right here. This was the time between building the new array and selection sorting. So that's 6 seconds, right? And here's the time between building the new array and the quick sort, 5 seconds, right? So it is 1 second faster at that point, which is not a big deal, but certainly could be a big deal the larger the array size gets. So these algorithms do have actual effects on time values when you start analyzing them. And again, this isn't the most accurate way to do this, but I thought it'd be kind of fun to just sort of show that.